Hey, welcome back to Hypotheses in Statistics. I want to remind you of some vocabulary to start us off. We're dealing with a lot of words about hypotheses, and we need to understand precisely what they mean. So we have an alternative hypothesis. Despite the name, this is the main working hypothesis of the statistical theory, and we have a standard notation for it, HA. We have a null hypothesis, that has a standard notation too, H0. The null hypothesis is counterpoint to the main working theory. It says there is no effect at all. Then we have an opposite hypothesis, which is the reversed claim. If we say men are taller than women, the opposite hypothesis is women are taller than men. The opposite hypothesis is not usually going to be one that we talk about very much. I introduce it so that people don't get confused about what the null hypothesis is. If you understand that there are two different ways of contradicting the alternative hypothesis, it makes it easier to understand what the null hypothesis is. A hypothesis test is a very careful and very procedural method for deciding the difference between an alternative hypothesis and a null hypothesis. Basically, we have two ideas about what might be true, and we have to figure out which one of them is right. And that's the job of the hypothesis test. It depends a whole bunch on the data that you get. You collect the data, you do some analysis. That analysis is called the hypothesis test, and then you declare which of these is right. And the result of the hypothesis test, at least the one that we're usually looking for, is the rejection of the null hypothesis. Because the alternative hypothesis is our main point, and the null hypothesis is the counterpoint to that says there's no effect at all. When we reject the null hypothesis loses, the alternative hypothesis wins, and then we say, oh, basically, we've rejected this and we've proven this. Actually, to be completely precise, we say we prove this to a statistically significant degree. So it's not an absolute proof in the sense of 2 + 2 = 4, but it is a proof in the sense that we have strong, significant statistical evidence in favor of this hypothesis that we made. So you may be looking at this hypothesis and think, well, once I look at the data, it seems like hypothesis testing is totally trivial and easy. So let me try to convince you first that hypothesis testing is not easy by looking at a little example. So let's suppose that we have a drug and it treats a condition. And the condition is dangerous, and so we have a certain mortality rate if you don't use the drug. And we have a certain mortality rate if you do use the drug. Okay, so let's imagine that we do a very, very careful job and we design this experiment and we get this really nice kind of double-blind trial, and we design an experiment correctly. And then in the experimental group of the patients who had the drug, some of them died. And in the experimental group of the patients who didn't have in the control group who didn't have the drug, well, some of them died, and we get a proportion. So we get a proportion, which is the mortality rate in the experimental group. And let's just say, for the sake of argument, that it's 1%. And we get a proportion, which is the mortality rate in the control group. And let's just say, for the sake of argument, that that's 2%. And let's say this is out of 500, and let's say this is out of 400. These groups don't always have to be the same size. All right, so is that a slam dunk? Well, maybe not. You see, 1% of 500 is just 5 people. 2% of 400 is just 8 people. So it was 5 of these people and 8 of these people who died. It certainly looks like the drug is useful in doing its job because remember, this is a probability of death. And so we want it to be low. So if it's lower in the experimental group, then that's really good. So it looks good, but it might not really be a big deal that it looks like because the sample size is kind of small. We don't know quite what to make of this. And there is always a danger. In all of these statistical testing ideas, there is always something that we need to worry about, and we need to worry significantly about this. What if that was just due to chance, right? What if these 8 people just happened to already have something going on? What if these 5 people, what if the few others who didn't die, maybe, what if they just got lucky? You know, what if whatever circumstances, like life is full of dumb luck, right? Life is full of coincidences, and maybe this 5 out of 500 versus 8 out of 400, maybe that's just some sort of coincidence of these numbers. These people just happened to get lucky or unlucky, and so it's not necessarily correct to jump to the conclusion that this drug is really useful. Now, this is really kind of scary when you think about it from the point of view of what can science do? Like we use the drug, we did a controlled trial, none of our samples are biased, and we get the result, and it's 1% versus 2%, and we're like, okay, thumbs up. Let's make everybody, let's use this. Let's use this drug in the real world. But well, yeah, maybe not, right? Maybe not, because maybe this is just simply due to chance. So this is the problem with statistics, and it is a problem with science generally, that maybe the results are due to chance. And when I say maybe the results are due to chance, this should make you mad, right? Because what I'm saying here is that maybe we really don't have the reason to believe the things that we seem like we have the reason to believe. And so when I'm saying maybe it's due to chance, maybe what I'm really saying is maybe the null hypothesis is actually true. So this seems a little bit contradictory, because let's think about what the alternative hypothesis would say in this case and what the null hypothesis would say to contradict it in this case. In this case, the alternative hypothesis would say the probability of death in the experimental group is going to be lower than the probability of death in the control group. Then the alternative hypothesis will say the probability in the experimental group is going to be lower than the probability in the control group. And here we are looking at these probabilities, and oh, well, the probability in the experimental group is lower. Doesn't that prove the alternative hypothesis? Well, only because I've used my notation a little bit imprecisely. And now let me be a little bit more precise with the notation. This probability here is an experimental probability that measures the sample. This is a sample proportion. This is a population proportion. I should not actually be using the same symbol for both of them. These are p hats, and these are p's. These are statistics, and these are parameters. These are sample proportions. These are population proportions. And so, yes, I know that there is a relationship between the experimental sample proportion and the control group sample proportion. There's an obvious relationship between them. But can I infer that there is the same relationship between the population-wide experimental group and the population-wide control group, which are more theoretical things because we haven't actually applied this drug out to the whole population yet. So this is predictive, right, and hypothetical. So it really isn't yet demonstrated that the alternative hypothesis is true, even if we collect this data. And that means that there must be something hard to do, something confusing that still remains to be done, because we're looking at the data, and the data is clearly pointing us in one direction, and I'm saying still, maybe it's due to chance, still, maybe the null hypothesis is true anyway. Now, I want to do another example in which I'm saying it's not quite so easy, and then we're going to look at, well, what are we going to do about this? Because basically what I'm doing now is I'm asking you to be skeptical of all scientific results, and that's not how we're going to leave it. We have to see the problem before we can understand the solution to the problem. So let's look at a simple political poll. So the alternative hypothesis is going to be, I'm going to state this kind of imprecisely. It's going to be more Americans favor Biden. Now, depending on when it is you're watching this video, this might be talking about the Democratic presidential primary in 2020, or it might be talking about the presidential election of 2020, or it might just be really dated. But okay, so more Americans favor Biden. So the probability here is going to be greater than 0.5. And here I'm just using p, but what I mean by p is the probability that you or anyone favors Biden in this primary or the presidential election or whatever. So the probability is going to be, so let's suppose that we do a survey, right? So we survey and we get 520 out of 1,000 Americans what do? They favor Biden, okay? And so we get the probability, and that's the proportion, that's 520 out of 1,000. And now, so that's 0.52, which is 52%. But there's one small mark that I've left off the whiteboard, and it's probably the most important mark for you to understand here. That is not, this P is not that P, right? This is 520 out of 1,000. That's the sample. This hypothesis is about the population. This P and that P are not the same P. This is population, this is sample. This is a parameter, this is a statistic. This is a P hat, right? So is this a slam dunk? If I survey 1,000 Americans and 520 of them favor Biden, then can I say more than 50% of Americans favor Biden? Well, no, I can't infer that because I know that more than 50% of my sample do, but I don't know necessarily that that generalizes. And it might be, might be 55, it might be 49, it might be 30. Could it be 30? I don't know. What are the chances of that? I don't know. That's kind of hard to say. So, so just having this information in the sample doesn't give us an automatic slam dunk that the hypothesis is true, because the hypothesis is about the whole population. So I want to say here, maybe the results are due to chance or coincidence. It's the same maybe that's on the other side of the board. And then again, with that maybe the null hypothesis is true. I didn't clarify what the null hypothesis would be in this case. Let's do that next. But maybe the null hypothesis is true. If the alternative hypothesis is a statement that more than 50% of Americans favor Biden, you might think the null hypothesis would be the counterpoint, fewer than 50% of Americans favor Biden. But that's not actually the null hypothesis. That's the opposite hypothesis. The null hypothesis is the statement of no effect, which is the statement of parity, which in this case is the statement that exactly 50% of Americans favor Biden. It's the even Steven exactly in the middle. So the null hypothesis is actually the statement that exactly 50% of Americans favor Biden. And maybe it's true. Maybe even in the face of this data, maybe it's true, right? I'm not saying before we did the experiment, maybe it would have been true. I'm saying even after doing the experiment, we still have to entertain the possibility that the null hypothesis is the real truth, the real explanation of what's actually going on in the world. And why did we get 20 extra people in favor of Biden? It was an accident, right? It was just dumb luck. It wasn't because our sample was biased or anything. It was just simple dumb luck. Because every time you call a person, it's a different person, and maybe you just get lucky, get unlucky, whatever. So these two things show us a basic problem with all of statistics and all of science. How do we make inferences that the hypothesis is true in the face of evidence that the hypothesis is true? So let's look at again, and let's ask the right question. So much of mathematics and so much of life and so much of science is really about asking the right question. So we do this controlled trial. Only 1% of those taking the drug die in the trial. Only 2% of those not taking the drug die within the trial. And now I'm saying maybe the results are due to chance. So what is the right question to ask here? The right question is, if somebody says, maybe that's due to chance, maybe that's a coincidence, think about me flipping the cards and then, oh, you got the right card. Maybe that was due to chance. Well, then the right question is, what are the chances of that, right? What is literally the probability of that? So the right question is, what are the chances? This has to be like the old sci-fi show, right? Where the captain says, what are the chances of that? And the robot, the annoying robot that always has the answer says, it's exactly 1 in 700, Captain, right? It has to be like that. We have to not only say, what are the chances in the rhetorical sense, we have to say it in the mathematical sense of, let's actually calculate what are the chances of getting results like this if the null hypothesis had been true. So again, we have the same question. Maybe these results, 520 out of 1,000, are due to chance. Maybe they are. But we have to ask the question, what are the chances? Oops. What are the chances of that? In other words, what is the probability if exactly 50% of the Americans actually favor Biden? What is the probability of getting a result skewed like this in the scenario that the null hypothesis is actually true? In this example, if the null hypothesis were actually true and this drug were actually useless, and we did 500 and 400, what is the probability of getting results showing us this level of difference? What is the probability of getting something like this? So this probability is a key to probability. And learning to judge this probability is really about how skeptical you are, which is about your alpha. So let me write some vocabulary for what this probability is all about. So this probability, the answer to this question, what are the chances, is called the p-value. And it is a central concept in all of statistics. Understanding the p-value is one of the main jobs of the course, and it's not an easy job because the p-value is a very subtle idea. So the p-value. The p-value is the probability if the null hypothesis were true. Well, let me spell that out. So if the null hypothesis were true, of getting results as compelling as the given data. It's a probability, so it's a number between 0 and 1. And it's the probability, but it's often expressed as a percentage. Like if you get 0.07, then we often express that as 7%, but that's okay. It's a probability, it's a number between 0 and 1. And it's the probability of getting results as compelling as you did if the null hypothesis were true. It's the answer to this question. What are the chances of that? What are the chances that the data would have come by coincidence if indeed there were no effect at all? So given no real effect, the p-value measures the chance of seeing an illusory effect comparable to the true data. And that might seem super abstract, but it's a very natural way of thinking if you get your head in the right spot, right? So I'm gonna shuffle a deck of cards and then you're gonna pick a card, okay? Now, if I get the right card, if I get, like, if we do some sort of magic trick and you pick a card, and then if I actually get your card and I win this game, then there are two explanations for that. One kind of positive and one kind of negative. The explanation, which is the alternative hypothesis, is there is something going on here, like the professor or the magician either read my mind or did some sleight of hand, or like there is actually some real thing going on. The other possible explanation is this simply happened by coincidence because there are only 52 cards in the deck, and so it was 1 in 52 coincidence. So with this competition between two theories of what happened, on the one hand, there really is something going on. There really is a real effect. And on the other hand, there is no effect whatsoever. And what I'm looking at, what I'm observing, which is impressive, is actually just the product of a coincidence. With these two competing explanations, then which one you pick depends on how probable that coincidence is. If I called the coin flip and you said, okay, it was heads, and oh, magically it's heads, then we all understand that like that's not very impressive, because in the case of coincidence, that would happen 50% of the time. So the p-value there is 0.5, right? 50%. That's not very impressive. But in the case of the cards, then that coincidence is much less likely, right? Which argues in favor that there must be something else going on, some sort of sleight of hand, or maybe he's really psychic, or maybe it really is magic, or something like this. So what judgment we make about which theory is plausible has to be informed by how probable we think it is that that result would come as a coincidence. And that's what the p-value is measuring. So with the coin flip, the p-value is 50%, right? Even if I'm right, then after the fact, we look at, but maybe it was a coincidence. And what is the chance that it would happen by coincidence? Well, it's 50%. So that means it's not impressive. And I'm really just not going to buy into that. But with the cards, then if I get it right, what is the chances that I could get it right by coincidence? The null hypothesis means there's nothing going on, it's completely random, and the result is due to coincidence. So what are the chances of that? Well, it's 1 in 52, which is approximately 1 in 50, which is 2%. So there the p-value is 0.02 with the cards. The p-value is 0.02. And 0.02 is like, that's not very likely, right? 1 in 50, that's not a very likely outcome to come by coincidence. So as we weigh the competing theories, on the one hand, the theory that, well, this was due to some real effect, this is really something going on, that's the alternative hypothesis. As we weigh that against the null hypothesis, the key to making the distinction is, well, what is that p-value? What is the probability that we would get that if we were just as a consequence of coincidence? And if that p-value is super low, then we would say, I don't believe that. That's not credible. That's not plausible that that would happen by coincidence. There must be something else going on. So the p-value is what we use to ultimately resolve the hypothesis test. And let me explain how. So just in a sort of qualitative language. So if the p-value is very small, then the null hypothesis is not credible. Basically, if the p-value is really small and you ask me to believe the null hypothesis, you're asking me to believe that an outrageously unlikely coincidence happened. And I don't believe that. If the p-value is large, then the null hypothesis is credible. In order to believe the null hypothesis, I need to believe, for example, that something of a 50% probability must have happened, but that's easy to believe. So yeah, that's still credible. So I would still think the null hypothesis is credible. So if you are able to measure the p-value, then using the p-value, you can decide whether anybody should ever believe in the null hypothesis. And that is the secret to deciding the difference between the alternative hypothesis and the null hypothesis. If science is going well, then we can measure the p-value exactly. We can report the p-value. And on the basis of the p-value, we can say, now, this null hypothesis is not credible. I'm going to kick that one out. And then only the alternative hypothesis remains as a plausible explanation for the data. And we can say, okay, the alternative hypothesis is demonstrated. So this is the p-value is the central tool by which we score the data for its quality and then decide which hypothesis is credible in the end. And so, of course, there's one huge thing that I still need to teach you, and that is, on the basis of your data, how do you calculate the p-value? How do you calculate that? Because what are the chances? That's super hard to do. Well, it's not super hard, but there's some learning to do. And so what we need to do next is I need to teach you how to calculate a p-value, and we'll do that in an upcoming video.